Good afternoon. I'm going to spend a little bit of time talking about embedded AI at what we call the very edge, which is really on devices which are very small, battery-operated devices, and about a processor called GAP8, which is based on the RISC-V ISA. So I work for a company called GreenWaves. We live in France. In the French Alps, actually, and we're a small fabless semiconductor company, so we're interested in making and selling chips. It's very clear that there's a lot of interest in edge AI. It's something which is in all of the newspapers. We talk about it all the time. And really, the reason why everyone's interested in edge AI is because if you pull everything back into the cloud, then you start to have a lot of congestion in the data center. You also spend a lot of energy doing that. And people also are rather worried about privacy. If you pull a lot of video streams into a data center, then there's that data becomes very available and is communicated. And there's also a decision latency problem. If you want to act on that data and do some step, then you need to do that local to the data so that you can actually take a decision and do something with that data quickly. What I'm going to look at is, that's kind of the edge. And the edge at the moment, I would say, is things like cars, it's things like video cameras, it's perhaps gateways. I'm going to look at what happens when you start to do that at the very edge, what we call the very edge. And that's where something is wearable, it's probably battery operated, or power is difficult to get to it, so it's expensive to install if you have to power it. You have to pull cables, you have to bring a workman in to make holes, and you end up spending more money than the sensor itself. Or it's distant from power, it's sitting in a field somewhere, looking at a leaf or looking at an insect or something of that sort. Or it's very difficult to service. It's in a location where you don't really want to try and get power to it because you can't add that power to an existing piece of equipment. What problems do we have to solve when we're producing a device like that? Well, one of the things that we find with AI is that we have probably three different states in an edge AI device. One is we're doing nothing, we're sleeping, we're waiting for something to happen. So we have to be very frugal at that point. Then, once we actually see something happening, we probably want to do some pre-processing on the information that's coming in. So if it's a vibration signal or something of that sort, then we want to move from maybe a time domain to a frequency domain or something of that sort, some kind of processing that we do. Then we actually want to do the inference step, and that's going to be a step where we're manipulating a large amount of data and doing a large amount of calculation on that data, which produces a result which is probably quite small. It's like, there is a problem, there isn't a problem, there are 10 people in the room, something of that sort. And at that point, we then want to communicate that, perhaps if it fits the reason why we want to communicate, because really it's great if we don't communicate, because if we don't communicate, then we don't use the power that communication is going to use, and that's going to use a lot of power to communicate. So there's a load of different types of algorithms we're having to run, and a load of different types of compute states. The other thing which we're finding in inference, definitely in the AI area, is that the domain is changing all the time. There's a new paper every month, that's the paper of the month, and everyone's going to say that type of way of doing NN is fantastic. So we talk about binary networks, or we talk about whatever it is the flavor of the month. So we've got a rapidly changing AI task, and as GreenWaves, I don't really want to be an expert in accelerating what was great last year. I want to accelerate what's great now. So we set up all of these different tasks, and now we've actually got to map a processor to those tasks. So we need to be able to scale our consumption to the workload in a certain task. We need to be able to dynamically scale the processor. And then we're going to be interested about, actually, once we've dynamically scaled, how much absolute energy are we actually consuming in that state. And then finally, which is really, really important as well, is being able to flip between those states as fast as possible. Because during the period of transition, we can't do anything, because the resource isn't available yet. So it's very important that that happens quickly. So we've produced a product which we believe enables this AI to the very edge. We call it GAP8. It's a very integrated MCU. It's very little support chips around it. All of the power management is integrated into it. And it's basically the combination of a controller core, which is the RISC-V core, with an 8-core parallel compute cluster. Those cores are tightly coupled to a shared memory area, and that allows that to be used like a calculation engine. But it's a programmable calculation engine, so we can adapt it and use it for a number of different types of algorithms that are parallelizable. That compute cluster, we believe, delivers about 20 times better power efficiency than state of the art for devices that are doing signal processing or AI at sub 100 milliwatts. In fact, the top consumption of GAP8 in its cluster when it's running flat out is about 75 milliwatts. So that's really GAP8 doing its most, and that's the sort of thing that we would do for that kind of thing, which is actually an autonomous nanodrone. So it's a nanodrone that can actually navigate, has a CNN inside it. That's kind of high compute load where you've got a high frame rate and you're doing that kind of work. Then the second thing it is very agile. It's able to move between different states, so it boots in under half a millisecond. And it can move between the different compute states and change its frequency in its domains very, very quickly. Very fast wake up. When it's actually doing nothing, it's down at 1 microamp. So it's state-of-the-art MCU level of power consumption. Finally, because it's programmable, it's flexible. So we can address all of these different types of algorithm, and we can also address the changing world of AI. So I've got an example of the energy efficiency of GAP applied to a certain problem. This was actually a benchmark that was released by ARM last year, where they had a CNN graph that was trained on what's known as CFAR10. CFAR10 is a load of little images in 10 different classes, so things like car, house, dog, cat, that kind of thing. And you train your convolutional network on these images, and then you want to present one of these images, and the convolutional neural network will interpret this new image and say it's a dog, it's a house, whatever. This was a graph the CNN graph that was what's known as highly quantized, which means that the data was reduced in precision. So the precision of the data was 8-bit. And basically, they ran it on an STM32F7, which is an M7 core, and they were able, in running that core at 216 megahertz, to do an inference in a tenth of a second, which you can work out to the number of cycles, which is 21.4 million cycles. We've actually restated the active power of that chip to something out of the datasheet of the STM32H7. From that datasheet, we've got a figure of 60 milliwatts, so it's going to be consuming 60 milliwatts during that tenth of a second that it's doing the inference operation. Now, if you run that on GAP, you can see that we reduce the number of cycles down to 1.5 million cycles because we're exploiting parallelism in the structure. That allows us to drop the clock speed down to 15.4 megahertz to do exactly the same inference in the same amount of time. So we ported exactly the same graph, 8-bit quantization, all the rest of it. But that allows us to drop the core voltage, and we drop the overall power consumption during that tenth of a second down to 3.7 milliwatts, which is about a 16 times reduction. And now this is fully programmable. We haven't used any hardware element. We've just used the natural properties of the cluster. If we pump the cluster up to 175 megahertz, which is its maximum speed, then we actually do the inference 11 times faster in 8.7 milliseconds, consuming about the same amount of power, 70 versus 60. Now, we also, within the cluster structure, we have a specialized block which can do convolutions, certain types of convolutions, because hardware blocks are always have their limits and constraints. But it does a 5 times 5 convolution on 16-bit fixed point data in a single cycle. So that's 25 multiplications, 25 additions, accumulating into 32 bits, in fact. If we switch that on, then we drop the number of cycles down to 460,000. We can drop the clock speed down to 4.7 megahertz, and then we deliver an active power consumption over that tenth of a second of underneath a milliwatt, 0.78 of a milliwatt, which is a 75 times power consumption improvement. Now, we're definitely not an M7 core. We can't do a load of things that an M7 core can do. We don't run Linux. We don't do things like this. However, for our subject, which is doing content understanding, signal processing in an edge device, which is battery operated, we believe that this is fairly unique in the market. How do we deliver it? Well, there's a number of different things. It's never one thing that actually gets you power consumption. It's lots of different things that gets you power consumption. The first thing we have is that we have across all of the cores a uniform instruction set that we've extended, right? So RISC-V gives us this great ability to be able to take some core instructions that were compatible with the tool set, but also to build our own extensions. So there we've added things like DSP operations, so saturation operations, clipping, zero cycle loops, these kind of things. We've also added SIMD instructions, and we've also added bit manipulation. The efficient parallelization. So parallelization's great, but your algorithm is always going to be driven by the moments when you're not able to parallelize. The sequential portions of your algorithm, which is known as Amdahl's law. So however much you speed up the bit that's parallelized, you're going to be driven by that. Well, we need to reduce that as much as possible. So that means we need to be able to spin off a task onto all of the cores as fast as possible, hit a barrier and then stop the cores when they've finished doing their work, because they may stop at different times, and save power at that point. And then also restart once we've got to a point where we can actually schedule off another task across the cores. What we do there in that is we do all of that in hardware. So all of the task scheduling, all of the mutexes, barriers are all implemented in hardware, which means we can spin a task and have it running on all cores in 3 to 4 cycles. Once it's running, if a core finishes, it hits a barrier, the next cycle it's clock gated, so it's not consuming any power. Once all of the cores hit that barrier, they all wake up on the next cycle. So one cycle wake up between them, which means that we can actually parallelize an algorithm that goes down to about 70 operations in its parallel portion, which means we're very effective in terms of those kind of algorithms. We then make use of the fact that we're parallelizing all of these things which are happening on the cores in the cluster. There's the same loop, so it's the same working set of instructions. So we put them all into a shared instruction cache. So we only do one fetch from the memory, and then we deliver that instruction to all of the cores. That's 30% of your memory movement is instruction fetch. So we just cut that by 7 times 30%. Finally, these pluggable blocks that we can add into the cluster structure, which act like cores. They see the memory like cores. They can run at the same time as all of the other cores, but they give us the ability to optimize, from a power perspective, certain operations that are really dominant. A convolution is the most dominant. 80% of the operations in the CNN is a convolution. So it's very important, that dominant operation. And then finally, all of the power management side of being able to switch on these blocks, switch them off quickly, is a really important portion of the product. Finally, all of this would be great, but if you can't program it, that's a big problem. So we basically support C and C++ across the entire architecture, so there's no need to recourse to assembly language. We've extended GCC. We have a GCC-based tool chain, and we've extended GCC with the optimizers using all of the extended instructions that we've added. We have a visual-based IDE using Platform I/O, which allows you to have a nice visual-based environment based in VS Code. And finally, we have a code generation tool which we call the autotiler. In the chip architecture, we have no data caches because mostly we're operating on stream data. The autotiler actually is kind of a software-based data cache or streaming data cache. It's a code generator, so you model what you want to do, you model where the data is and how you want it moved around, you model what your kernel operation is, and it will spit out code which provides you with an API which directly calls your kernel function, moves the data around, moves the output back into the right place. So in a single line of code, you can generate, for example, a convolutional there. In fact, in a single line of code, you can generate a convolutional plus pooling plus ReLU for a certain data set with a certain input size, output size, filter size, and so on and so forth. Just one call. And that's our generators for a wide range of algorithms. So we do convolution layers, but also traditional signal processing like FFTs or fill filters or matrix operations, all of these kind of things. So the next question is, so where do you use it? So there's a number of different use cases which we're finding traction with GAP8. We've already been shipping, as I said, the hardware development kit for nearly a year now, since last May. So we have a number of customers operating in different areas, and these are all things that we've seen that there's interest or there's active development on. The whole area of counting people or objects, be they people within office spaces, so taking a picture, counting the number of people on it, sending that information back, that's really super interesting from a facilities management perspective. For example, a manager comes to the facilities manager and says, hey, I never can find an office in this meeting room in this office. And the facilities manager can say, well, that's because this 12-person meeting room is always being used by 2 people. So that kind of data can save a lot of money in those kind of environments. In the industrial area, the whole area of preventative maintenance, doing high-speed vibration monitoring, doing fault detection on that. The higher speed you can do those vibration monitoring systems, most of the interesting things are happening at very high frequencies, so it's interesting to have something that's capable of handling that kind of data, and then not transmitting it off chip, just doing all of the inference necessary to spot some problem. Also, infrared is another interesting area in industrial fault detection. In consumer products, there are a number of opportunities to use this kind of product in dolls, in small robots, in toys of various different types. We can run face detection algorithms on the product. We can run face ID algorithms on the product, so we can spot if someone using something is the same person or the owner or whatever, and adapt our behavior, adapt the behavior of the device to that. On our stand over there, we also have a micro drone which autonomously navigates. So that's actually on the stand, and you can come and have a look at it. Smart buildings, so glass shatter detection. So is it a bird? Is it a stone? Is it a hammer? Is someone breaking in? Gunshot detection, scream detection, all of these kind of areas of sound processing. The whole area of keyword spotting on GAP8, we can fit quite a large vocabulary keyword set, plus beamforming, echo cancellation, noise reduction, all in the same chip. So because we have this DSP capability, we don't need a separate DSP to do that. From a security perspective, this is a kind of there's two kind of hierarchical kind of ways that we can use GAP. One is to use, say, some very simple sensor which is very low powered, but often generates false positives. So passive infrared sensor would be one of those, right? It can spot that something's moving, but it doesn't know whether it's a person or a fox or a dog or whatever. And the false positive is going to call a call out from a security center, which is then going to result in someone driving there or even having to call the customer, which is a cost. So what we can do is we can wake up GAP with that sensor, take a photo, check, is it a human being? It is a human being, send the alert. It isn't a human being, go back to sleep again. And then the inverse of that, which is that we might have some kind of high-resolution camera where we have a very sophisticated AI solution that's tied to that, that's processing high-resolution data. And there what we can do is we can use GAP to spot all the time what's going on and see if there's something interesting, an interesting state, and then wake up the larger system. And we have a number of use cases in that area. And that whole area of wearables is also something where we're seeing quite a bit of traction with GAP. GAP's origins are very much anchored in open source. We use elements which come out of a project from ETH Zurich and the University of Bologna called Pulp, which stands for Parallel Ultra Low Power, which is a 5 or 6 year project looking at parallelism and how parallelism can be used to deliver low power. Our CTO is still an active member in that project and in fact a researcher in ETH one day of his week, and was one of the founding members of the Pulp project. And Pulp itself uses RISC-V. So it uses the instruction set architecture and produces core designs which are using and extending that instruction set architecture. We then take those building blocks and we engineer something around our market vision, which is this market vision of battery-operated edge inference devices. This allows us to be very, very capital efficient and really focus in all of our engineering spend on the things that make us special, and also at the same time, anything which we use where we augmenting that or enhancing it or finding bugs in it, we can feed that back into the community. So it's very much an open source type project, even though, as I like to say, the difference between open source software and open source semiconductor is that when you press the compile button, it costs a lot more money when you're making a chip. GAP8 is available now, so you can buy GAP8 or GAP8 development board called GAPwino. It can be bought through our site or through Seed. We have a full open source SDK which is on GitHub. All of these generators that I've been talking about are actually in open source, so you can modify that source code. We also are actually selling engineering samples through our website. We'll actually be in production with production qualified chips in Q2. Thank you very much. Any questions? I rattled through that fast, so we've got time for questions.